Okay, we're recording. So before we get into the math, reminder about the attendance quizzes. It's on Canvas. I sent a detailed email about it yesterday. There should be a quiz of today's name. Today's date is the name of the quiz. There's one question. This is the answer. Make sure to enter this. Make sure to confirm your score, right? It's not enough to just enter your answer. I don't know if you have to hit submit or something like that, but make sure that it is fully submitted and that you see that you got the points for your entry. And time's very short at this point. It does disappear deliberately 2 minutes after the start of class. That's my way of enforcing punctuality. Anyway, you've got 48 seconds left, so make sure to get that done. Okay, jumping into the math. We're going to start talking about how to visualize functions. Y'all have seen graphs previously. What I've got here is kind of a lot of formality. And I find that's not a particularly useful way to get what we really need to understand. So I'm going to go straight to the examples. And we're going to start with what I know y'all are already very familiar with. This is the graph of a single variable function. So the graph of a single variable function goes like this. Think of the x-axis here as kind of being sort of the domain, kind of, sort of, in some sense, right? And for every one of those input values, that comes out of the domain. You plug into the function, you see what comes out, right? So that goes into the function. What comes out is y. And then you kind of smash those together, right? You take the input x and the output y, and between the two of them, that gives you this point x comma y. That's a point on the graph, right? X coordinate, y coordinate. And altogether, the collection of all such points is the graph. All right, everybody see how that works? I mean, I know y'all have seen this a million times, right? The point to this is not, does the picture look familiar? The point is, you see the process, right? So that's the process by which that is the construction called the graph construction. Okay. All right, so what we're going to do now, okay, well, let me not get ahead of myself. Let me give you a couple of different ways to think about this. Have their moments. One way to think about this is that, again, we have a domain, which is the x-axis, kind of, if you will. It's R1. And think of the function as telling you how far to push upward at every point on the x-axis. Right? So I start off with this line that is the x-axis, and according to what the function says, if you just push all those points upward corresponding to what the value of f of x is, then that green curve will get pushed up to produce this other curve, which is the graph. That's a nice way to think about it. What I like about this way of thinking about it is it justifies why typically graphs of single variable functions are one-dimensional. They're curves. Curves are intrinsically one-dimensional. They don't have area or volume, right? They have length. They're curves, one-dimensional. They're one-dimensional because they are produced from a obviously one-dimensional thing, namely a line. Okay. All right. Here's a different way to think about it. Morally equivalent, but just kind of a different point of view. The graph is the set of solutions to the equation that you get when you take your function f and you set its output values equal to a new variable. That's what the graph construction says. Graph construction says, okay, you got this f, x's go in, f of x is what goes out. You don't have to give f of x a different name. It is entirely a choice. Now, it's a choice that you practically always did every single time in single variable calculus classes, right? But the point is, you don't really have to. The act of deciding to take those output values and call them by the name of a new variable is a different point of view on how the graph construction works. Okay. All right. Now, with all of that said, let's sort of think through the same thing, but now for a multivariable function of two variables. Okay, so our domain is two-dimensional. The inputs that are going to go into this function, x and y, you can think of the domain kind of, again, a little sloppy, but whatever. Think of it as being the xy plane down here. Right. And for any given x and y, put those inputs first. Plug those x and y into the function. That'll give you an output value z. Put that next. All those coordinates. By the way, let's take a moment to recognize how weird this is. We're taking input coordinates and output coordinates and smashing them together to make the coordinates of a new point with 3 coordinates. It's a little strange, right? But that point is then a point on the graph. And again, the graph itself is the collection of all such points. And in this case, I argue that would be a surface like this. What do you think? Everybody good? All right, so again, 2 different ways to think about it. You can instead think about this as, well, look, the function just gives you the instruction of how far should I push upward. Sorry, colors. How far, plug into the function, that tells you how far you should push upward from the xy plane. And by the way, this is, I think, pretty good intuition for why the graph of a function of 2 variables is a surface. Because we start off with a domain that is a 2-dimensional surface. And every point in this 2-dimensional domain surface just kind of gets pushed upward by, different amounts at different points. But if you start off with a 2-dimensional thing, sort of shoving it upward, you would sort of expect to get a 2-dimensional result. Thus a surface. Okay. Again, an alternative way to think about this, I think really useful. Starting off with a function, right? Domain, target, formula. The graph is what you get when you set the output values equal to a new variable. In this case, x and y are both inputs, so I'm going to use z as my new variable name to call the output. And that's, again, nice and pithy, right? When you're doing algebra and you want to write down the algebra for the graph of a function without having to think about the picture and stuff like that, just say z equals. Now you got a graph of whatever your function is. Everybody on board? Everybody see how this is just a rip-off of what we did in single variable? It's all the same ideas morally. Okay, so great. Now, it would be reasonable to kind of suspect at this point that maybe this is how we visualize functions in multivariable calculus. I mean, this construction is like almost the only picture we ever draw of single variable functions. The graph, every picture you draw of a single variable function to speak of in single variable calculus, they're all graphs. Right? It's so familiar, it almost feels like you have to, isn't that what a function is? Which, by the way, no, it's not. Right? But we use it so almost universally, it feels like it is. Okay. I'm sorry to say that is not going to be the case in multivariable. In multivariable, the graph construction has a real nasty problem. You might even already see this coming. But you notice how we're almost out of dimensions already, right? We only have 3 dimensions to work with reasonably, right? We can't visualize 4 dimensions. I don't believe anyone who says they can, right? So if I've already used up all of my dimensions, what do I do if I have a function that has 3 input variables? In other words, let me say this differently. The second most trivial possible case, right, of a multivariable function. The most trivial case of a multivariable function would have 2 variables. This is the second most trivial possible kind of multivariable function. And, we have 3 input variables. We have 1 output variable. 3 in, 1 out. That makes 4. You'll notice here the points on our graph, 3 input coordinates, 1 output coordinate, and it lives inside of R4, and I can't even pretend to be able to draw that. Crash and burn. Right? Does everybody see the problem? And this is a nasty problem. Drawing multivariable functions is going to be pretty different, like not just artistically, but conceptually and mathematically, very different from drawing single variable functions. In single variable, you always draw the graph. It's the perfect, oh my gosh, it's so perfect. If you think it through, the graph of a single variable function, it lives in 2 dimensions. We have 2-dimensional paper. That's perfect, right? The graph itself is a 1-dimensional curve. I have 1-dimensional pencils. It's awesome, right? You could not ask for a better set of coincidences. So graphs are fabulous for single variable functions. They are, in the most trivial case, barely acceptable for multivariable functions. And in anything beyond the most trivial case, it's crash and burn, complete loser. Right? Okay, so alright, so this presents a kind of a problem that we have to kind of undo some thinking that kind of we got accustomed to in single variable calculus classes. In single variable calculus classes, they very often conflate a graph with the function whose graph they're talking about. And they're importantly different. We're going to see lots of multivariable functions. We're going to see pictures of multivariable functions, and many of them will not be graphs. If you conflate these things, you're going to have massive problems, right? This stuff's not going to make you, you're going to look at a picture and think of it as a function and try to interpret it as a graph, and it just, if it's not, then you're out of luck. Okay, so make sure to separate these in your mind. A function is an algebraic object. The graph of a function is a geometric object that we create by a very particular prescribed construction. Is that cool? Okay. All right. Oh, related note. Sometimes students will use the word graph as kind of a synonym for the word picture. Again, in single variable calculus, you can get away with that because most of the pictures are graphs. In this context, you really can't. It's going to create a lot of confusion. If you point to a picture that's not a graph and say, well, let's look at this graph right here. Okay, wow, that's a real problem. Okay. So heads up about that as well. Okay. Let's see some other ways to draw multivariable functions. I like this one a lot. It's going to start off feeling kind of disappointing. I'm going to try to turn you into subscribers to this idea. What I like to call the literal picture of a function. Literal in the sense that if you have a function, you can take the domain, in this case R3, and I can literally draw a picture of R3. And then I can take the target, R1. I can literally draw a picture of R1. What does the function do? Well, the function takes points out of the domain and drops their images into the target. Well, I can literally represent that. I mean, I can take a whack at representing that anyway by drawing an arrow that supposedly, suggesting that points are coming out of here with images landing over here. Picture. It's a picture of sorts. That's a very disappointing picture, right? I mean, we look at the single variable graph and we're like, oh, this was awesome by comparison. I see a shape. The geometric features of this shape tell me about the algebraic properties of the function, namely its derivative, right? The first derivative of the function tells you about the slope, which is a geometric feature on the graph. The second derivative of the function tells me about the concavity, up or down, on the graph. So this has a picture, and we all have strong intuition for how to relate the geometry of this picture to the calculus of this function. And that's fabulous. And where's the picture here? Where's the shape? Right? I mean, it's a real letdown. Okay. So I'm sympathetic to that complaint, but now I feel like again, I was making a point for rhetorical purposes. It was a very unfair point. I was comparing apples to oranges. This is a function of 3 variables, and I was comparing it to the graph of a function of 1 variable. Let's play apples to apples. Disappointing picture here for a function of 3 variables. No picture, crash and burn failure for the graph. Now which do you like better? Right? In a choice between nothing and disappointing, you got to give the nod to disappointing. Yes?
Can we talk about the notion of continuity?
Oh, yeah, that's a big topic, and it's something that we're going to mostly just kind of wave our hands at. And there's a lot of really interesting math down that road, but it's not really quite what this course is about. So most of such questions we're going to kind of hand wave yeah, right. Yes.
What information can you get out of a real picture?
Yeah, great question. That's a perfect segue to my next thing. So let me try to persuade you that this is actually more useful than, this is better than nothing. Right? So, okay, here's my case. Let's imagine that I am looking at a point like this one. So I've got this point A there. By the way, for whatever reason, I like to think of myself as being at the corresponding point in the dome. Wherever we're looking, I like to that's me. I'm sitting right there. Okay. And of course, then there's this output point, f of A. Here's a reasonable question that we might want to ask. Here's a reasonable question that we are going to be asking a lot, and that you will ask a lot in outside of this class. If I were to take off from this point and start moving with some velocity, and again, here's me, right? And if I move from this point, in some direction with some speed, we represent the corresponding velocity with a vector. It's not a weird scenario. That's me. I might want to move. This is just me moving. Nothing weird. Well, where I am determines the inputs that go into this function, and I hope it comes as no surprise if you change the inputs. If you are in the process of changing the inputs to the function, the outputs to the function are going to be changing also, and so there will be a corresponding output velocity. I don't know what it'll be. I'm arbitrarily going to make up some vector, but if this point is moving with some velocity, its image will be moving with, some velocity. Now, how do we determine this vector? Well, that's actually a longer conversation. That's going to take us a while. We won't be answering that today. My point is not how to answer this question. My point is that I can actually represent the question. Don't know about the answer, but I can represent the question on this literal picture. This literal picture is arguably the perfect way to describe the question here. Does that make sense? Yeah. So it's an opportunity for me to talk about what I might be doing in the domain, and what correspondingly might happen in the target, and it's something. Right. Okay. Next, let's talk about level sets. Again, there is this is a fairly formal definition. We'll come back and point to this a little bit, but I don't want to start with this. Let's start with some actual examples. So here's an example. We've got a function here. By the way, let me remind you, functions are trios: domain, target, formula. Okay, so there's our function. The way we describe a level set is you pick some output. I'm going to pick 1 just to get the ball rolling. Given that output, I want to ask now, what are the corresponding input points? What points over here in the domain will this function give this output for? This exact chosen output. Okay, so I want the function, let's see, let me represent. I want the function to give me 1. So I want the value of the function to equal to 1. So I'm looking then at x's and y's that satisfy that equation. Oh, hey, how convenient. I already know what the set of solutions to that equation looks like. That's the unit circle. And so the level set is this unit circle. What do you think? It's a picture. By the way, you'll notice that this is taking place on the literal picture, right? I drew the domain over here, I drew the target over here, and we're doing business accordingly. But anyway, so the level set is this unit circle, and it's a picture of sorts. Now, is it the graph? No, absolutely not. Can I infer from like the slope of the level set? Can I infer something about the derivatives of this function? Absolutely not. That's for graphs. Right, that's calculus of graphs, and we're going to talk about the calculus of graphs in this class also. But this is a completely different kind of a construction. I did not form the graph, and I therefore cannot interpret it with how I interpret graphs. So we're going to have an entirely different kind of parallel calculus of level sets that we'll be developing later in the course. Okay. Now, by the way, you can do this for as many points as you want. Let's see here. Let's do this for the output value 2. For that output value 2, what points does this function take to 2? Let's see here. Said differently, what are the solutions to that equation, namely that equation? Well, again, it's a circle. It's a circle of radius square root of 2, old familiar high school algebra thing. So there's a different level set. Same function. You can draw as many level sets as you like. The more level sets you draw, in some sense, the more information you'll be representing in your picture as to what the thing looks like. How we doing? Okay, now let me point out that's all that's going on with this notation up here. And let's see, let me color code so this will fit reasonably. For a given, wrong color. For a given output, what we're going to do is we're going to look at all of the corresponding input points such that when I put them into the function, the value that I get out of the function is that pre-selected output point. So this is just kind of a formal way of writing down, take an output and look at the corresponding inputs. Everybody okay with that? Okay, now let's talk about the notation. Why do we call this F inverse? By the way, legitimate gripe. This function here is not even invertible. I certainly can't just go around assuming it's invertible. How can I write down the inverse function if the function's not even invertible? Absolutely. Good complaint. In this context, that's just not what this means. Sometimes mathematicians will borrow notations because they kind of conjure some of the right images, even if maybe they're not quite perfectly appropriate. So this kind of thing is not rare. What we mean by F inverse here is that we sort of start with an output point. We're starting with a point in the target, and then what gets produced is a set in the domain. So the process of constructing a level set kind of goes backwards. We start with an output. The resulting level set is in the domain. So sort of backwards from what the function's doing. Does that kind of, I mean, again, it's a little bit of an abuse, and it's not an invertible function, and that is not the inverse function, but it conjures this image of it kind of going backwards from the direction of the function. Okay. All right. Okie dokie. Here's my favorite example of level sets, and that's contour lines on topographical maps. I don't know if any of y'all have done any hiking at any point. If you have, you've probably seen topographical maps and the little curvy squiggles like on my shirt here, right? Which I got lucky. I did not seek out such a shirt. I was just walking by and oh my God, that's a topographical map. I just had to buy it, right? But contour lines look kind of like this. The big idea is that every contour line represents a bunch of points on the land where the altitude is a prescribed value, 300 feet above sea level, for example. So every point on this green contour line represents where the altitude, the value of the altitude function, is exactly 300. And then, of course, you notice, that's literally exactly a level set of the altitude function. So the reason I like this is that it's something that, I personally happen to have just a little, I'm not like a huge hiker, but I've got a little bit of experience. I've used topographical maps, and I've done some hiking, and I've got a healthy respect for certain things that I can see on a topographical map. So for example, if I wanted to get from here to the top of the mountain there, I know that is an aggressive choice. This is an aggressive trail to take. You're just going straight up the steep part of the mountain. Now, how do I know that that's steep there? Well, each one of these lines, let's say, represents, let's say 100 feet. As I go along this purple curve here, I'm going to be gaining 100 feet of altitude over very short horizontal distances. It's really steep. Right? In my younger days, that would have been on the table. Nowadays, I am far more likely to do that. I gain the same total amount of altitude, but notice at every part of the hike, I'm gaining those same 100 feet of altitude, but over greater horizontal distances, which means it's not as steep. Does that make sense to everybody? So there's, so it's not a graph. The slopes of these lines are not derivatives. It's not the usual kind of intuition about, in terms of how it relates to calculus, but there's useful information to be had there. And it's a two-dimensional picture. And now, as you're trying to decide if you like this or not, let's just observe, if you were instead to make a graph of the altitude function, you would have a three-dimensional, it'd be like a surface, right? You could make it out of paper mache or something, right? But you'd have a surface that's ultimately a big three-dimensional thing. You'd be hauling a box basically around on your hike with you. And nobody wants to do that, right? Much easier to take a two-dimensional thing, namely a topographical map, aka a bunch of contour lines, aka level sets. You can fold that up and put it in your pocket. Or you can conjure one on your screen, right? And probably apps and stuff like that. So it's really much more practical. Everybody on board? I'm going to point out, this is an actual topographical map. Let's see here. I downloaded this from a government website. I think it's the USGS, U.S. Geological Survey, or something like that. And they have free topological maps, by the way. It's pretty cool. So I did this hike when I was about y'all's age or so. It's in Colorado. And a couple of things that again, I will point out that we can see just off of this picture, right? This is basically a bunch of level sets of the altitude function. Right along in there, crazy steep. Again, look how close together those lines are, right? Each one of these lines, I think I remember each one of these lines represents 40 feet of altitude. Each, the tiny little horizontal separation between these lines means that you gain 40 feet of altitude over very short horizontal distances. FYI, this is extremely steep. It's about like this, honest to God. Right? It's like 75 degrees. When you're up there, you would swear it's a straight vertical drop because it's really scary to kind of look over the edge. It's about 1,200 feet from where you're standing to where you would stop rolling if you fell. Right? That's a lot of, it's legitimately scary. So anyway, you can see that by the contour lines being close together. I also like to point out while I'm on this page that if you look at the trail down here, it does this thing called switchbacks. And switchbacks, again, is a smart thing. It's a way of taking a steep hike and turning it into a longer but less steep hike, right? So you could imagine if you went straight up the mountain, well, you're gaining 40 feet every, what's that, about half an inch or so on the map. But because of the switchbacks, instead of gaining 40 feet over half an inch, you're gaining 40 feet over, that looks more like inch and a half. So that's 1/3 the steepness. It's much more palatable. And by the way, much appreciated when you've already, by the time you get to this point in the hike, you've already done about a 2,000 foot climb. And you're tired. Oh, and there's very little oxygen up there. You can't breathe. So shallow hike is much better than a steeper hike. Okay. All right. So lots of information. Thank you, level sets. Is that everybody happy with that? Yes.
Is one level set just one of the lines?
Yep. Yeah, that's right. That's right. So what I've drawn here in green is just one level set. Maybe that's where the altitude is 500 or something. And then this one here would be 400, 300, 200, like that. Or whatever. And that is one of the downsides of using level sets. You then have to kind of write over to the side, or maybe you label on the level sets, 500, 400, 300. Otherwise, you can't technically tell if this is a mountain peak or if it's the bottom of a pit. Yeah, absolutely. Everybody good? Okay, here's a cool fact. Notice, given a function, now we're going to look at a function of two variables here. The graph is what I get by setting it equal to z. The level sets are what I get by setting it equal to a constant. Two different constructions. Right? Setting it equal to z, setting it equal to a constant. Well, I'm going to make the smart alecky observation here that if I set z equal to a constant, in effect, I have set f equal to a constant, kind of indirectly. Right? If you set f equal to z and then z equal to c, altogether f has been set equal to c. And so you get a level set. So let me write this down then. Level sets can be thought of as relating to graphs by this process of setting z equal to c. And now geometric appeal, if you set z equal to a constant, that's a horizontal plane, you're effectively taking a horizontal cross section. So level sets are horizontal cross sections of graphs. Everybody buy it? Let's see an example. looking at this function right here. I've already forgot what colors I used. Okay, the level sets are in blue. Level set. The level sets are circles. The graph. Now keep in mind, same function. Same exact function. The graph is what I get when I set x squared plus y squared equal to z. Oh, what is that? Well, technically, y'all don't have the tools yet for me to be able to argue what that is. We will do that very soon, probably be on Friday. I don't think we're going to quite make it today. But I'm going to claim to be explained later. Hopefully you're willing to trust me at the moment. That graph is a kind of a bowl like this. Okay, so now let's ask, does this statement hold? This says that the level sets are supposed to be horizontal cross sections of that graph. Is that true? Well, if I take horizontal cross sections, just setting z equal to different constants, whatever. Take horizontal cross sections of that graph, and lo and behold, indeed, you do get circles that look just like the level sets. So literally, level sets are horizontal cross sections of graphs. And I did just commit a little micro math crime. I'm going to fess up and fix it in just a second. But for the moment, let's keep it pithy. Level sets are horizontal cross sections of graphs because these blue curves are pretty much the same as those blue curves. Everybody happy with that? Okay, confession. Let me get rid of the... I mean, technically, these blue circles aren't quite exactly the same as these blue circles. These blue circles live in 2 dimensions. They live in the XY plane. There is no Z coordinate. These blue circles live in a 3-dimensional world, right? They came from this surface, the graph surface that literally is in 3-dimensional space. Points on these cross sections have a Z coordinate. These don't. So, okay, this is super picky and quibbly. And in circumstances in which that distinction is clear, you don't have to talk about it. And I think, again, in most situations, for most purposes, it's fine to just keep it simple. Horizontal cross sections of graphs are level sets. Is everybody happy with that? Sweep this whole Z matter under the rug. Okay. All right. Cool. Okay. Yeah. So we've talked now about several different ways to draw pictures for a function. Said differently, we have several different ways to relate algebraic stuff, functions, to geometric stuff, pictures, geometric objects. Single variable calculus classes inadvertently teach us a lot of really bad lessons related to this point because every picture you ever draw is a graph. And so they're usually really, you get accustomed to just kind of assuming that every picture is the same kind of a picture because in single variable calculus they are. And it's so easy to just, picture, graph, come on, it's all the same stuff. So you got to be really careful not to do that in this class. And this example is, by the way, I basically lifted this example out of an old test question. In fact, I've done several old test questions that are morally equivalent to this example. And we're going to talk through all the details. The upshot, though, is going to be you've got to be really careful what kind of construction you're if you say you want to relate a geometric object like a line with an algebraic object like one of these functions, be careful which construction are you talking about. They are all different. They give you different functions. And they all have what I'm going to call different kinds of calculus. Okay, let's start with an easy one. Looking at this line as this equation, let's ask, what is the function g for which one of the level sets is that line? Okay, wait a second. Let's think this through. How do I take a level set of a function? When you take a level set of a function is you set it equal to some constant. So I need to figure out how can I realize this algebra here as being some function equals a constant. Well, kind of an easy, kind of a freebie, because it is already written literally as a function equaling a constant. So boom, 2x plus 3y. Easy answer. Is everybody on board with that? So this line L is a level set of that function g. Okay. Now, by the way, that's not the only such function. So here's another thing I could do. This is you could argue this is silly, but I'm not saying you should do this. I'm saying this is on the table, and there are situations where this will be useful. I could have said 2x plus 3y plus 1. This line is a level set of that function also. You just got to be careful which level set you're talking about. It's when I set this equal to 7 that I get an equation equivalent to the equation to the line. But nevertheless, it is a level set of this function. Let me be clear. It's a level set of this function. It's just a different level set because I wrote down a different function. Does everybody see what happened there? This is just, it's arguably kind of silly, but for whatever reason you want to do that, you could. Okay. All right. What about the graph? For what function is this up here a graph? And it's tempting to say it's not a graph. If it was a graph, it would say y equals. This doesn't say y equals. I could make it say y equals, though, right? Just solve for y. As long as you're doing, reversible legal algebra, as long as the resulting equation is truly equivalent, which in this case it would. If you just literally solve for y, what you would get is let's see here, color choices. This y, when you solve for it, would give you that. And notice that this function, set it equal to y, that's what it means to take a graph. And again, equivalent algebra, that means that this is the graph of this function is this line. Everybody happy? Okay. All right. This, you don't have any choices. There is at least if you want to view y as being a function of x, a graph in that sense, this is the only function for which the graph would give this line. But I will emphasize, you don't have to solve for y. You could solve for x and view this line as being the graph x equals, f of y and then it'd be a different function. Okay. All right, and then lastly, parameterizing. Well, y'all know how to parameterize. Back to chapter 1, right? So y'all can think through, pick your favorite point on this line, doesn't matter. Pick your favorite direction vector parallel to this line, doesn't matter. And do the usual construction from chapter 1, and that'll create a parameterization. So this is one such parameterization that describes that line. Okay, so again, you got to be really careful about this sort of stuff. If you apply the calculus of graphs to this function, you're going to get a bunch of garbage nonsense, right? So, for example, if you try to find the slope of this line by taking the derivative of this function? Nonsense. It just straight up doesn't work. Right? The idea of slopes equaling derivatives, that's part of the calculus of graphs. Right? So you have to use the function for which the curve in question is a graph. And if you take the derivative of this function, then yes, indeed, you will get the slope. Because again, you're looking at a graph, and you're using the calculus of graphs, and that works. Does everybody see what I'm talking about there? Okay, it's a very common mistake. I used to see lots and lots and lots of catastrophic errors that students would make because they're using the wrong kind of calculus for the wrong kind of function, that relates to the picture by the wrong kind of construction. Right? So super duper careful about that. Now let me point out another thing. A lot of students will look at this and think, that looks really easy. My gosh, the algebra. Shoot, I could do that algebra when I was in middle school. Right? Mistake. What makes these questions hard is not the algebra. What makes these questions worth entertaining at all is not the algebra. The purpose of these questions is to make sure that students are able to make appropriate distinctions between these things, between these different constructions, to make appropriate use of the terminology. Don't say graph if you mean level set. Don't say function if you mean equation. Stuff like this, right? So what makes these questions hard, and again, I've done this on exams several times, no comment about this semester. I frankly have no idea what I'm going to put on the exam this semester. I haven't even started thinking about that. But what would make a question like this on an exam hard is that you got to interpret the question exactly as it's stated. You have to answer the question exactly as it's stated. You have to give me what the question has actually asked for. You have to use the terminology correctly. And again, subtle distinctions. Don't say function if you mean equation. Stuff like that. So there's a lot of stuff to be very, very careful about. And that's what makes these questions hard. Right? So here's a couple of examples of mistakes that I see. If the question was, here's an equation, and what function has a level set that is that line? And if the answer that you give me is you write this down, if this is your answer, 2x plus 3y equals 6, the question asks for a function. That's not a function. That's an equation. Question wanted a function. This is the equation that you get by taking a level set of a function. I didn't ask for the equation of the level set. I asked for what is the function whose level set is this equation. So it's different, right? It's not the same thing. And again, the purpose of these questions is to make sure that you're careful and can make proper distinctions on these terminologies, and make sure to actually answer the question as stated. Does everybody see the concern there? It's real easy to mess that up. So you need to plan to kind of drill yourself on the terminology. There's an adaptation process, by the way. I'm sure you're all accustomed to fairly casual uses of these terms. You're going to have to fight that, right? And make stricter, more careful interpretations of the terms. Okay. All right, let's see. We are, I've got, wait a second. I can't see the thing here. I have 30 seconds. We'll draw the line here. I'm sure I owe you 30 seconds. So see y'all later. Have a good rest of your Wednesdays. See you on Friday.